This is going to be part 3 to reaction kinetics, and today we're going to look into kinetic energy. In the past, we have used kinetic energy and looked at how it was used in reactions, but today we're going to go a little more in depth with it. So in the past video, we looked at a graph that looked something like this. On the x-axis, we had the progress of the reaction, and on the y-axis, we had the enthalpy. Keep in mind that enthalpy is energy. It's the potential and the kinetic energy. So in this video, we're going to look at a graph that looks something just like this. As you can see, instead we have kinetic energy of the reactants on the x-axis and the number of molecules on the y-axis. And so this kind of graph is called a Maxwell-Boltzmann distribution curve. So what this graph shows is the average kinetic energy of reactant molecules. As we can see, right here on the highest point of the graph, this is the average kinetic energy of the reactants because it has the highest number of molecules with that amount of kinetic energy. What we also learned in the last video was activation energy. It's the amount of kinetic energy that molecules need to actually get over that sort of hump, which is an energy barrier, in order for the reaction to even occur. So in this case, we're going to place our activation energy just right here, just as an example. So that means that all the molecules in this space have enough kinetic energy in order to proceed with the reaction. And as you can see with this graph, only a very small percentage of all the molecules in this curve actually have enough kinetic energy to get over this activation energy. So now that we determined only a very small percentage of molecules have enough activation energy to actually proceed with the reaction, we can figure out how can we actually speed this up? How can we get more molecules to get over that activation energy hump so that the reaction will proceed faster? Well, one of the main things that we can do is increase the temperature. As we learned in the last videos, increasing temperature will increase the reaction rate. But why? Well, looking at this graph, we can figure out exactly why. First, let's just say that this current curve we have right now is at 50 degrees Celsius. Now, let's say we hypothetically raise the temperature of this reaction to around 60 degrees Celsius. Let's take a look at what the distribution curve will look like then. Now, we can see that many aspects of this graph has changed. For one, we are able to see that the average kinetic energy of the reaction molecules has increased. They now have more kinetic energy in them. But more importantly, we can see that even more molecules have surpassed this activation energy point. This means that there are more molecules with enough kinetic energy to get over that activation energy in order for the reaction to occur. And as well, we must note that this activation energy has not changed. It has stayed the exact same through any temperature. It is simply the amount of molecules that have surpassed that activation energy that has changed. Remember that activation energy can only be changed with the addition of a catalyst. With this graph and information, we are able to come to this general rule that with every 10 Celsius increase in temperature, the reaction rate is doubled.